Hello and welcome to Calculus 3. We are going to start with Chapter 12 overview. This is something that we do in Calc 2, but just in case we are going to go through all of the concepts. And those are parametric equations, polar coordinates, and calculus in polar coordinates. Parametrization is going to be very important for us because we will need to describe a curve in three-dimensional space. And that will be done through something that's called vector valued function. We will use it also, and we have a whole chapter that depends on that. And then we will also use it in last chapter, chapter 17, when we do vector fields. We will have to parametricize the curve C for line integrals. So parametrization is going to carry at least 2 chapters on its back. Other than that, polar coordinates are important because a lot of integrals that you really don't want to do in rectangular coordinates might be easily done in polar coordinates. So conversion to polar coordinates is important. And then we are going to learn 2 three-dimensional coordinate systems that are built on top of polar coordinates. One is called cylindrical coordinates. The other one is called spherical coordinates. And they both have polar coordinates as a base. So if you don't speak polar coordinates language, well, half of chapter 15 or whatever is out, or 16 is out for you. So a lot of future material depends on this stuff. So let's go and talk about first parametric equation. So the easiest way to understand parametric equations is to just understand that parametric equations break dimensions apart. You have a system that is xy or xyz as a unit. Parametric equation separates dimension x from dimension y from dimension z and gives them all their individual equations. So here is an example. Say you have an equation that says x equals 3t plus 1 and y equals t squared minus t plus 1, for instance, right? So this is what you have. So this is known as the set of parametric equations in 2D. Now 2D, in this class, we are going to use the capital R and we're going to put a square on it. So double bar R with a square on it. This means 2D. You will have R cubed for 3D. See, the real line R, right, is just x-axis. If you have 2 of them, x and a y, then it's R squared because you have real numbers on x-axis and then real numbers on the y-axis. So x and a y, 2 of them, it's going to be R squared. Add z to it, you'll have 3, so R cubed. So if you only have x and a y variables, then it's 2-dimensional system. We denote that as R squared. And they represent 2D because you have x and a y. Now, both of these equations is bubble on top, which is great. Now, looks like we're back in business. Reconnection successful. I will see. So, the parameter t, you can think of it as time. So, for this particular problem, I can say t equals 0. That's the beginning of time, right? Big Bang, let's say. So what do you have? Well, you will have your x to be 3 times 0 plus 1, which equals to 1. And your y will be 0 squared minus 0 plus 1, which is also 1, which will produce a point 1, 1 in xy realm. So when you assign a value for t, you get a location in space. And that location in this case is 1, 1. You can say, all right, so let's say this is time in intervals of 1 second. So what happens with the 1 second as the 1 second passes? Okay, well, I can calculate x for 1 second, which is 3 times 1 plus 1, which is 4. And then y equals 1 squared minus 1 plus 1, which is 1. So now the object is at 4, 1. So what we see here is that as I let the time pass, right? 0 seconds, 1 second, 2 seconds, 3 seconds. It will keep giving me location where the object is. Now that can be a bug, it could be an electron, it could be you, your car on a GPS two-dimensional plane, right? Applications are endless. We just want to understand that there is a parameter t that at the same time adjusts the values for x and y, and it can be used to trace the path for x and y in two-dimensional space. Now, what you can do is you can take these equations and put them together into a single equation and see what that equation is in x and y by eliminating t. So now I'm just going to pick something less annoying. Let's say x is equal to t minus 2 and y is equal to, I don't know, t squared plus 3t minus 1, whatever. So if you want to work out the equation in x and y, you will solve whatever equation is easy. You will solve for t, and you will plug that into the other equation, replacing all of the t's. So now y is equal to x plus 2 squared plus 3 times x plus 2 minus 1. And now you just massage this with algebra, get x squared plus 4x plus 4 plus 3x plus 6 minus 1. Y equals x squared plus 7x plus 9. It worked out to be this quadratic polynomial. So we have a set of parametric equations which we solved by eliminating t, and we came up with what we call Cartesian rectangular coordinates equation in, as you can see, R2, right? It is two-dimensional equation. So we are able to work this out. Now, we don't care how complicated these equations are. If you are able to solve for t and plug in the other equation, then you can come up with whatever equation is there. Now, there is this really cool set that we will be using a lot. X equals, let's say, 3 cosine t, and y equals 3 sine t. Now, some of you might already know what this is, and it's okay to yell out if you know it. What is this? Anyone? Come on, it's okay. I don't bite. Hard. Still shy. Okay, it's day 1, so it's fine. This is a circle radius 3. Now, let's prove that. So from the top equation, we have that cosine t is equal to x over 3, from where t is equal to inverse cosine of x over 3. And now when you plug that into y, you get y equals 3 sine of inverse cosine of x over 3. Now you might remember from the trigonometry course when you had to simplify these pointless problems. They had no purpose. It was just, filed under mathematical gymnastics. Hey, look what I can do. Well, now they're useful, right? So we have to simplify this, and the way you do it is you change this function to match that one so they can cancel as inverses. So you draw the triangle using the cosine, if this is your angle over here. Cosine is adjacent over hypotenuse. That's how you know this is adjacent over hypotenuse, so you know what goes where. which using Pythagorean theorem makes this 9 minus x squared. So it's not arbitrary. You use Pythagorean theorem to come up with the third side. And now you rewrite the problem, except this time you have sine inverse. And a sine inverse is going to be opposite, which is the square root minus x squared, divided by hypotenuse, which is 3. At this point, these cancel, and you are left with y is equal to 3 times square root of 9 minus x squared over 3. So now these cancel, and you are left with y equals square root of 9 minus x squared. Square both sides, y squared equals 9 minus x squared, and here it is, x squared plus y squared equals to 9. Yay! Circle. Now you might argue, well, why, right? This equation is inherently easier than having sines and cosines and bringing trig in and then having two separate equations. No. Sorry, but no. This equation here for the circle is equation in x and y, and it's not a function. So when you draw a circle and you use your vertical line test and you strike that through the circle, you see that it crosses the line twice, which means not a function. Here, I'll write it in blood, not a function. Now, what does that mean? Well, that immediately means that calculus for that is going to be a living nightmare. Derivatives will use the implicit differentiation, if you remember that from Calc 1 at all, right? And for integration, your integral is integral of f of x. You can't even do the integral for this unless you are prepared for some Calc 2. You have to do what? You have to cut this thing in half, right? Then use just the upper half, and remember to double your result. And your upper half is square root of 9 minus x squared, which you integrate using what? Exactly, that's correct. 10,000 people said trigonometric substitution. So, it's just so many people that the stream is not canvas. Whoa. So, yeah, you would have to integrate using trig sub. Holy nightmare, right? Now, when you consider your parametric equations, look at that. Cool, right? You have parametric equations and they're both functions. You can do whatever you want, right? Easy. So, the great thing about these parametric equations is they can take expressions that are not functions and break x and y dimensions so that each individual equation is a function. And when you have that, you can do the rest of the calculus easy. So as I said, it's going to be a base for chapter 14. All of the chapter 14 will be done with parametric. And then later on, chapter 17 will have this as a base. Now, a few more things about parametric equations. Number one, because we have a parameter t, or theta, or s, or whatever, it gives us an extra degree of freedom. So now we can have orientation. You see, when I draw a circle, let's say this is that circle radius 3 that we have. If I have this as x equals 3 cosine t and y equals 3 sine t, and t is in between 0 and 2 pi, this will trace the entire circle, but guys, this is new now. The circle will have orientation counterclockwise. Counterclockwise, if you put cosine on x. You can test this. What is happening at time equals 0. See, at time equals 0, cosine is, or 0 is 1, so 3 times 1 is 3, and a sine of 0 is 0, 3 times 0 is 0, so it's 3, 0. So this is time equals 0, that point where the 3 is, on the x-axis. If your time is pi over 2, that's about 1.5 seconds, 1.57 seconds, whatever. So if your time is pi over 2, your cosine is 0, and sine is 1, so you have 0, 3. So this is t equals pi over 2, and you can see that as the time progresses from 0 to higher numbers, you are going counterclockwise. Now that's going to be completely reversed if you swap sine and cosine in your parametric equations. So for the next circle of radius 3 in xy plane, x equals 3 sine t and y equals 3 cosine t, with t going from 0 to 2 pi again, you are going to now have clockwise orientation. So it's going to go this way. So clockwise, counterclockwise. Now, you might be, in this attitude state, yeah, whatever. Oh, hold on. In chapter 17, all of your definitions and theorems will say if you have a smooth curve, blah, 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 oriented counterclockwise. Oriented counterclockwise. You have to be careful, because if it's oriented the wrong way, it's going to add an extra minus sign, and your problem is wrong, right? So, right now, this orientation has no purpose, but later on it will. So be mindful that the orientation is always, and you can write this in your notes if you want to, orientation is always in the direction of increasing t. Orientation of parametric equations is in the direction of the increasing parameter t. Orientation is in the direction of the increase of parameter t. Great. So that's our orientation, and yeah, we're done pretty much with parametric equations. They're not that special. They're very important, but they're not that difficult. By the way, this story here of me plugging in t equals 0 and t equals 1, you can do that to graph your parametric equations. You will be, if you want to graph parametric equation, you will, instead of having only x and y columns, you will have t x and y columns, and then t will be producing ordered pairs. You put the ordered pairs, and you strike a line through the ordered pairs, like a coloring book, except you don't have to color, right? Just connect the dots, and you're done. So that's the short story of parametric equations. Now we do also have the derivative of parametric equations, because, see, parametric equations are great to take things that are not functions, right? The expressions that are not functions, and break them into the set of functions. So if you want to calculate the derivative, and you want the derivative because you want the tangent line, because tangent line measures the change. That's the goal of calculus. Calculus is a study of change. So since you want to study the change, and the change is measured by the slope of the tangent line, and the derivative is the slope of the tangent line, you want to know how to calculate dy dx. Now, when you have your dy dx, you will just divide top and bottom by dt. So what you actually get is it's dy over dt divided by dx over dt. It's the simplest thing possible. So if you want this written as a formula or whatever, you can say for parametric set x equals f of t and y equals g of t, so you have two different functions that are both function of t, then dy dx is going to be I made a mistake. G prime of t divided by f prime of t. You gotta swap them, guys, because your y, right, dy dt goes on top, and that's your g prime, right? So a lot of grade goes and dies right there, right? When you put f on top. G is the one related to y, so maybe you want to put some kind of mark there to make sure that you have your that's straight. I think now we're done with parametric equations. So we talked about graphing, we talked about orientation, we talked about the derivative. Yep, we're done with this stuff. All right, so let's talk about polar coordinates. So polar coordinates has two kind of parts. First part is introduction and pre-calculus. Second part is calculus. So polar coordinates, and this part is intro, meaning algebra pre-calc. So what we have for polar coordinates is the different way to get to a point which still lives in xy plane. You see, when you have a point somewhere in the xy plane, like that, in order to figure out its location, you will go out on the x-axis until you are right under the point, and then you will go up on the y, and you will just measure how far you went in both directions. So in this case, for this xy point, we went 1, 2, 3, 4 units in x direction, which is red, and 2 units in a y direction, which is blue. So we label this point as 4, 2. So to find the location on a 2D plane, all you need to do is to travel along x until you are above or below the point you're looking for, and then you just go in a y direction and just count how far you went. Now, polar coordinates work in the same xy plane, but they get to the point in a different manner. You see, if you have a point, let's say somewhere over here, to get to that point, you actually go out and then you swipe an angle to reach it. So now this would be the radius, and then there will be the angle theta to get there, which gives us r comma theta for our new coordinate system. Now let me demonstrate a few of these. Let's say you have 3 and pi over 3. So to graph this point, this location, you will go 3 units out, and then you will look for 60-degree angle. Swing this there to get to the point 3 pi over 3. So this angle over here is 60 degrees, which is your pi over 3. It's a very simple concept, right? All you need to do is to go out on positive or negative x-axis, right? You know because you will see positive or negative number for r. And then you will go positive or negative to get to the point in terms of the angle. So some kind of, I hate the formula diagram, but it is a formula diagram, I guess. If you go like this, we go out, positive r, we go out, negative r. So you can have a positive or negative r in your point. You will go on a positive x-axis or a negative x-axis. Depends on what you have. Next, if you are on a positive r side, positive angles are going to go up. So this is your positive thetas, and your negative thetas are going down. If you are on the negative side, well, the positive angles are down. Because remember, counterclockwise is always positive angles. And the negative angles go up, negative thetas. Now, memorizing this is probably too much, because you can use common sense. If you know that all your positive angles are always counterclockwise, well, doesn't matter on which axis you are, it's always counterclockwise for a positive angle and clockwise for a negative angle. So you can always find it. But you know what? Here it is. It's a formula. So I'll put on a cloud. There you go. So now you can experience r theta, negative r theta, negative r, negative theta, and r negative theta. And obviously, each one of these will end up somewhere. Now, these four do not mean 4 quadrants. Be very careful about that, right? For x and y, when you have positive x and positive y, that's first quadrant. No questions asked. Negative x, positive y, second quadrant. Here, no. The quadrant is determined by positive or negative r, and how large is the angle. If I have r to be 3, depending on a theta, I can still land the point in all 4 quadrants, right? Pi over 4, first quadrant. 3 pi over 4, second quadrant. 5 pi over 4 would be here, in the third quadrant. You see, so if I'm adjusting the theta, I can go into any quadrant that I want. So these are not quadrants, these are the flavors that you can get. You know, vanilla, chocolate, strawberry, and chocolate chip mint. So those are the flavors of the combinations you can get. The size of theta will tell you how far you have to go. If the theta is, I don't know, 17 pi over 3, well, you're going to make few rounds and then land in a quadrant. So polar coordinates exist on top of the xy plane, but they do not use straight lines anymore of x and a y to determine the point. Instead, they draw the radius and then they use the angle, right, from the anchor point, which is 0, 0, from the anchor point to go to whatever they need to go. Now, this coordinate system is insanely good for anything that it's around in terms of graphs, and a lot of those pictures that are not functions. So first off, as we are learning the polar coordinates, we want to see the cheapest graphs that you can get. If you recall your algebra at all, you know that the cheapest graphs that you have in algebra is x equals a number, so x equals a. What is x equals a? in algebra? Very good. Yes. So it's a vertical line through A. And what's y equal A? Y equal B? It's a horizontal line through B. Great. So these are the cheapest equations that we get for the xy. So if you have x comma y, it's a point. If you have x equals a number, it's a vertical line. If you have y equal a number, it's a horizontal line. The question is, what do we get for polar coordinates? What do we get when I say r equals a number? R equals A. Well, let's talk about it. See, if you are trying to make the comparison to what you already know, and that's the way to learn math, you say, okay, x equals A is a vertical line. I see that A is always fixed, right, which is x value, and y takes on all of the possible values, in this case from negative infinity to positive infinity. So because, and guys, this is going to be very important to deal with planes in a 3D space. We'll see it. See, the variable that it's not mentioned, and negative 10 and positive million, are all of the values that you can possibly think of y will take in this case. And it's completely opposite here. Y is fixed, x takes on all of the values. So now, if my r is fixed to be, let's say, 3, what is theta doing?
0.
All of the values from negative infinity to positive infinity. So what does it create? It creates a circle of radius A. Now, if this is not the most amazing thing you've seen today, you have very interesting lives. Because remember the horror of an equation, x squared plus y squared equal a squared? Right? Clearly, writing a function, r equals a, r equals 3, gives you equation of a circle in polar coordinates. Well, that's a joke, right, of an equation. It's a joke of an equation. Much easier than this. And we'll see some equations for that. Now, let's talk about the other one, theta equals b. Well, in this case, you have all the radius, and angle is fixed. So it will be some angle b, and it's going to be a linear line that stretches infinitely, right? Because all r's from negative infinity to positive infinity are available to us, and they all have to be always fixed at the origin. Is it easy to have a line, a linear line, that it's not in the origin? Well, it's very easy. Y equal mx plus b, right? Is it easy in polar coordinates? Hell no. Polar coordinates are not designed for straight lines, right? Polar coordinates are there for circular stuff. So now in that aspect, right, we are going to understand that what's nice in one system is going to be absolutely disgusting in the other. That's the goal. These are not in opposition. They complement each other. All right? They complement each other. So what they do is one system is great for one type of equations, the other system is great for other type of equations. And I can demonstrate that now with very simple. So let's first take a look at the function, which is written as r as a function of theta. So this is our function notation, and I can give an example of r equals 4 cosine 2 theta. That's your function. So now r equals 4 cosine 2 theta is going to give us a picture of a flower as a graph. So you graph it, and it works out to be this. 4 petals, 4 units out on XY graph, this is what you get. Is this a function? Anyone, please. This is why I'm depressed all the time. No, I ask questions, no one wants to talk to me. I just like alone all the time. 30 people, everyone is alone. Is it a function? No, right? Draw anywhere. Draw the vertical line, it's gonna fail, right? So not a function. But look at its polar coordinates. So easy. Look at that thing. 4 cosine 2 theta. It's a joke, right? It's a joke. Now let's see what its counterpart is, right? The xy. For that, we need to be able to convert between the two systems. And a conversion is something that you must know, because you will have to convert from rectangular to polar, polar to rectangular, and these are bases later on for 3D cylindrical and spherical coordinates. So conversions are very important. So now to just quickly develop the conversion, you have your x distance, you have your y distance, you have your theta, and you have r. And by simply writing three basic trig equations, sine, cosine, and tangent, and Pythagorean theorem for this, you get sets for conversion. Really easy. If you write sine theta equals y over r, you get the equation y equal r sine theta. If you write cosine theta equals x over r, you get the equation x equals r cosine theta. Hey, we have our first conversion pair, and this is polar to rectangular. Because if you give me r and theta, I will give you x and y one at a time. So clearly this is conversion polar to rectangular. For this graph, if you write tangent theta, which is opposite over this, which is y over x, you can come up with the equation theta equals inverse tangent of y over x. And if you write Pythagorean theorem, x squared plus y squared equal r squared, you can come up that r is equal to square root of x squared plus y squared. These are lengths, so no need for plus and minus. What you have here is a conversion from a rectangular to polar. Because if you give me x and a y, I can get you r and theta one at a time. So by simply writing three trig equations and the Pythagorean theorem, you can come up with these conversion equations. So now we are going to take our friend r equals 4 cosine 2 theta and expand this and see what we get in our system. Now, this 2 over here is annoying, right? Because it will be exactly this, but the 2 is in there, so no, it's not that, right? So what we can do is we have to use a trig identity where cosine 2 theta is cosine squared theta minus sine squared theta. And now we can replace everything. So r is replaced by the square root of x squared plus y squared equals to 4 times. And now cosine, as you can see, is x over r. So we'll have to replace r again. And then minus y over r if you're replacing a sine squared. So I replaced cosine with x over r, and I replaced the sine with y over r. those came from this red. Right? You see the cosine is equal and sine is equal. Great. If you replace, guys, if you replace this cosine with the inverse tangent, then you have to go through that extra calculation of the triangle and so on. Try to look for these easy ways. So now I still have to replace r with the square roots. So I have a square root of x squared plus y squared. This should be absolutely disgusting when we're done, because you are not supposed to get a nice equation on the flower, right? Polar equation for it needs to be nice. XY equation is supposed to be disgusting. So let's see. We have x squared divided by x squared plus y squared here, because the square will kill the square root, right? We see it over here that r is equal to the square root, so r squared is equal to no square root on the other side. Minus y squared over x squared plus y squared. Great, has the common denominator already. So square root of x squared plus y squared is equal to 4 x squared minus y squared divided by x squared plus y squared. Now you can move the denominator to the other side by multiplying it. It picks up the power. You have an exponent 1 and exponent half. 1 plus a half is 3 halves. So x squared plus y squared to the 3 halves is equal to 4 times x squared minus y squared. And then that's it. From this point on, you can just cry. There is no way to solve this y equals everything else, because flower is not a function. You can't have y equals everything else. So you can deal with this, or you can deal with r equals 4 cosine 2 theta, right? Clearly, the polar way is the way to go, rather than having this really obnoxious equation on the other side. So again, what is beautiful in one system is going to be bad in the other, which is the reason why we have both systems. Mathematicians are lazy, right? We wouldn't have something that has no use ever, right? We go and we develop things so that the stuff is as simple as possible, which is why every next course you take is always an upgrade to the previous stuff and makes it. Those of you who took linear algebra, you already know that you can pack your entire Calc 1, 2, and 3 in a single equation, right? Those of you who already took linear algebra, you found that. And you said, wow, spent years of learning mathematics and now I have one equation, everything is packed into it. So that's what happens later on, right? So now we understand that there are mathematical functions which you guys learn and you can use in polar or rectangular, and you can swap between the two worlds. Now, what's happening is, wait. I love when I get the sales calls. I don't know if you pick up. I always pick up. But let's finish this. Hopefully they call again. So, what else? So now that we are that we understand that there are functions, and then there is this bridge between rectangular and polar world, we would like to see how we get to benefit from this. Well, one way is to have a simple equation when we have certain shapes like flowers and annulus and cardoid. So they would have simple equations. We saw this equation of a circle. It's a joke. R equals 4. Circle of radius 4. Simple, right? Now, the reason why we have this is to have easy calculus. So we have the derivative and integral, which are both derived in the course. And I mean, you can take a look at the textbook and see the derivation. I have to just fly through this, and we'll do I would rather do examples than the derivation at this point. The way you derive derivative, because you want your dy dx derivative, but you have polar coordinates, is you say that your x, I'm going to write it here and then I'm going to erase it because I'm just going to write the formula at the end. So you know that your x is r cosine theta and your y is r sine theta. Well, if you want your dy dx, in this case dy d theta over dx, d theta and d theta is cancelled, these are product rules, right? Because you have r as a function of theta, and then you have cosine theta, so that's a function times function. So if you work out the product rule for the top and the product rule for the top and product rule for the bottom, you will get these long expressions. So the derivative is not the most pleasant thing for polar coordinates, but again, it beats working with this. So, right, it's easier to find basic derivatives than to work with that monstrosity up there. So we have f prime of theta sine theta plus f of theta cosine theta divided by f prime of theta cosine theta minus f of theta sine theta. Now, as a student, because I learned through patterns and all of it visually, all I remembered was this. That's invisible. How about this one? This is all I remember. I only remember the top term, f prime times sine, because that's f prime and sine, and this is just the other two, and then f prime with the cosine, and then the other two. So that was the way I remembered it, but whatever. So this is used to calculate slope of the tangent line, because the flower that I drew earlier, right, is going to have a tangent line right here at this particular point. So what is the slope of that line? Well, you will use this formula here, and then you will have r comma theta, I don't know, 3 and 8 pi or 12 or whatever, and you will plug that in and you will have your m. For integral, we have to calculate area, because it's a definite integral, 1/2 integral alpha to beta. Guys, these are Greek letters a and b for angles, because the angle the formula is d theta. So 1/2 integral alpha to beta f prime of theta d theta. Oh, so not f prime, sorry, f squared. Squared. And these are your formulas for derivative and integral in polar coordinates. So now, let's say you decided to tutor math. You found, I don't know, a middle school or intermediate school student somewhere, and you are talking to this kid, right? And equation of the area of the circle comes up. We all know that's a equals pi r squared, right? And if the radius is equal to 3, then you say, oh, area is 3 squared times pi, which is 9 pi. And the kid goes, why? Say no more, right? Because this is the perfect opportunity for you to show off your integral, right? Because if you don't understand why water rolls downhill, well, let's go. You want to calculate the area of the circle from 0 all the way to 2 pi. That's a full circle. Can you come up with one pizza slice? Sure. 0 to pi over 4 is one pizza slice. Right? So you want the full area. Well, that's going to be 1/2, 0 to 2 pi. And now your function. Your function is r equals to 3. Wasn't that a circle in polar coordinates? Yeah, right? So 3 squared d theta. All you need to do is to integrate this. Well, that's easy. That's 9/2 outside. Integral of d theta is theta from 0 to 2 pi. That's 9/2 times 2 pi minus 0. It's 9 pi. Woohoo! And the kids is happy because now they're completely lost. Make sure that whatever I say you never do, okay? That's because I always pick the worst possible scenarios. So there you go. You see that integrating area of the circle, hey, circle was not even a function, but in polar coordinates is a joke. Now, what would it take for you to integrate the circle in using x and y, rectangular coordinates? You guys have to use trig sub. So good luck. All right? And you have to be really clever to pull that off, because you can't plug in equation of a circle into f of x because it's not a function. You have to know that you have to cut only half of a circle, right? So you will have only this much of a circle, and that would be square root of 16 minus x, no, 9 minus x squared, because our radius is 3, and that's just the upper half. So now your area is 2 times integral this and this. Well, I should have drawn the whole thing. This is 3 and it's negative 3. So from negative 3 to 3, square root of 9 minus x squared dx. So this is how you would find the, right? And now that equals, and then over here is trig sub garbage equals 9 pi at the end. You get the same answer, right? So it takes a long time, right, to do this in xy coordinates. Polar coordinates, boom, one step, you're done. And that is the reason why we learn these coordinates, to help us solve problems that are otherwise either impossible to solve, or there will be no way to integrate that flower. I mean, look at that equation. You can't even cut it in half or anything, right? Look at this. You can't cut this in half and then just pull up some trig. There's nothing you can do. You can just cry, right? But to place this into your polar integral and just integrate that, not a problem, right? You have to use trig identity to get rid of the cosine squared. But other than that, it's walk in a park. You have your so if you are integrating the whole flower, you want to see what's the well, it can be the first mechanical engineering application of today, right, of the course. You are designing the cookie cutter in terms of the flower, and you just want to know what the surface area is, because when you multiply the surface area of the flower, of the cookie cutter, times the height of the cookie, which is the cookie dough, you will get the volume of it, and then you would know what the nutrition stuff is on the amount of cookie that you have. It's mechanical engineering, actually, right? Plus some Rachel Ray stuff. Now, my favorite show. Why are you laughing? Get up. There's a reason why I'm this big. All right. So, We have 1/2 integral 0 to 2 pi, because you want the entire flour, you want the whole cookie. So that's 4 cosine 2 theta, everything squared d theta, right? So now, if you want 1 petal of this, well, you will multiply by 1/4 in front, right? Because he has 4 petals, and then you just want 1. But generally, you want the whole cookie. I mean, you're not a quarter of a person, right? You eat the whole cookie, you don't eat half or something. Like someone says, oh, would you like a slice of pizza? I mean, slice of pizza. Who eats a slice of pizza? You eat pizza or you don't eat pizza? It's a heavy category. I fold it in half. You haven't seen that method? The fastest method to eat the whole pizza, fold in half. All right. You learn a lot of practical things in this class. You just need to be here. Okay, so what do we do? Well, first off, 4 squared is 16, goes outside times 1/2, that's 8. That's gone. Integral 0 to 2 pi, and now I have the cosine squared of 2 theta d theta. So what you need to know to survive this course is the formula that you needed to survive the previous course, which is cosine squared theta is 1 plus cosine 2 theta divided by 2. So anytime when you run into sine squared or cosine squared, sine squared has a minus here, you have to use power reduction formula. There is no other way to solve these unless you memorized what their answers are. So now you will have 8, well, that divided by 2, now it becomes a 4. Integral 0 to 2 pi, and in parentheses you have 1 plus cosine 4 theta d theta. Because, look, formula, whatever input you have, it doubles it on the output. If your input is theta, your output is 2 theta. If your input is 2 theta, your output will be 4. So don't mess that up. And now, when you integrate this, awesome. 4 theta plus integral of cosine is positive sine, so we have sine 4 theta over 4, computed from 0 to 2 pi, and now it's just arithmetic, right? Please note that both of these will die when you put 2 pi for sine. Every integer value of pi, including 0 for sine, is 0, so they all die. You have 4 theta as the answer. Sorry, 4 times theta, 2 pi, which is 8. Pi minus 0 is 8 pi. So the surface area of the cookie, the flour cookie, right, is going to be 8 pi. So now that cookie, guys, is a 4-inch on one side, 4-inch on the other side. So that cookie is actually 8-inch, right, diameter-wise. And it has a surface area of 8 pi inches squared. Now you will multiply that by the height. Let's say the cookie is 1/2 inch high, whatever, right? So the volume of the cookie would be 4 pi inch cube. Now pi is, just call it 3. So if with the 1/2 thickness is about 12 cubic inches of a cookie. So now that you have the volume, you know how much, right, volume-wise, you can calculate other stuff, right? And you can work on packaging, right? Because there is also how many you can stack and all these kind of things. There's just a lot of good math that you can pretty much come up with anything that you touch. So that was our cooking portion of the today's show. Do we need to talk about anything else? I don't think. I think we're good to go. These are it. Parametric equations, polar coordinates, and then oh, actually, no. We will have a special lecture on that, 16.3, so we can wait. All right, so that's it for this. Bye.